This lecture will be on path analysis and invariance, and all the concepts we cover here will also apply to structural invariance. For this example, we're going to test whether this model is equal or invariant across both groups. Remember, you're testing a system of equations and a bunch of separate regression models. So for example, one model would be those in red, is whether beta 1 and beta 2, prediction on college connectedness, see college, is equal across the groups. In this case, whether parents pay or do not pay for their kids' college. It's important to remember invariance testing is basically testing whether those paths are equal across the groups. If they differ across the groups, that means that parents' pay status would moderate those paths. Typically, you want to follow a 5-step process when testing for path analysis and invariance. In your first step, you want to test the overall model and make sure that model fits well as a whole. Again, it's the overall model that you're combining both samples together. In this case, those kids' parents who pay and do not pay for college. The second step is you want to test whether the model fits well for each group separately. In this case, those kids' parents who pay for college and those kids' parents that do not pay for college. At this point in the model development, if the model does not fit well, what we'll typically do is modify the model so it fits well for both groups. But it's very important to remember, any change you make for one group, make for the other group. So if you add a path for the kids' parents who pay for college, you need to add the exact same path for those kids' parents who do not pay for college. The next model, here called step 3, is our configural invariance, often called our baseline model. This model is basically a weighted combination of both samples together. And this model also needs to fit well, and it's going to be compared to the path analysis model in step 4. So in step 4, your path invariance model is one where you constrain all the path coefficients to be equal across the two groups. Essentially what you're testing are all your beta and gamma coefficients equal across kids' parents who pay for college and do not pay for college. If your changing chi-square is non-significant, that implies the model is equal across both groups. In other words, all your beta coefficients and gamma coefficients are the exact same whether your parents pay for college or they do not pay for college. If that's non-significant, you could actually stop the model building process right there. However, if you have a significant change in chi-square, what that basically means is that one of your betas or your gammas are different across groups. And that's where step 5 comes in. Typically in this case what we'll do is look at your modification indices and figure out, okay, well if the model fit is significant, which path coefficients are constrained to be equal really should be relaxed and not equal across the groups. It's important to remember not to look at all the modification indices, but only those related to those parameter constraints. In other words, those betas and gammas that are constrained to be equal across groups. After you relax those parameter constraints, you continue that process until your changing chi-square is non-significant. Any paths that are different across groups, it can then be said that parents' pay status moderates those path coefficients. Just like with an interaction, which is basically what invariance testing is, if it's non-invariant or moderated, that basically means that your beta coefficients or gamma coefficients are different across the groups. Now we'll give an example of how to actually test this with an Mplus. Again, our first step, step 1, is to test the overall model. As you can see here, we have 3 variables predicting connected to the college, 1 variable predicting connected to the professors, and another variable predicting intent to persist, and then I'm correlating the learning orientation with problem-solving variables. It's just a very simple path model. As you can see here, our chi-square is non-significant, which is a good thing, and our CFI, TLI, RMSEA, and SRMR are all well within the acceptable standards. In step 2 here, we're going to test each model separately. As you can see here, the only new code we have is the useObs variable. And here it's useObs equals 0 on the left-hand side, and useObs parents pay equal to 1 on the right-hand side. Basically, all we're doing here is telling Mplus on the left-hand side only use those individuals where parents pay is equal to 0. The right-hand side, we're going to use only those in the sample where parents pay is equal to 1. Now here's kind of a dilemma that we would typically resolve if this were a real-life problem. On the left-hand side, when parents pay equals 0, you can see the model fit is not very good. So typically we would make changes to the model and then re-estimate it again. And do the exact same thing for the model on the right. Given that we really don't care about publishing this study or anything else, I'm not going to worry too much about model fit. But you can see just from these results that something is different across these two groups, that something is not invariant. The question is the path coefficients. Here's our configural invariance model in step 3. Really the only new code here is what's called grouping is parents pay, and then you have 0 equal pay and 1 equal no pay. Everything else in the model will be exactly the same. Again, remember, this is creating a weighted combination of both samples. So the results will not be the exact same as the overall model. Here's the model fit statistics for the configural invariance model. As you can notice, the chi-squares here are additive. So if you look at the chi-square for the pay model, with 4 degrees of freedom, the chi-square is about 19. For the no pay model with 4 degrees of freedom, that model is 3.289. Those sum to 20.655. Again, you can see the model fit for the pay model is much worse, which is also contributing to the much larger chi-square for the configural invariance model. As you can see, the CFI looks good, TLI is a little bit lower than we'd like, but the SRMR looks good, and the RMSEA is a little bit high as well. But again, typically we'd revise the pay model so it also produced a good model fit. Here we're going to test for path analysis invariance, which is basically step 4. The only really different code we have here is under the model statement. You can now see the 1 through 6, which refer to the parameter constraints. They want to be equal across both groups. The most important thing to notice here is you have one line of code for each constraint. Typically when you estimate this model, you'd have C college on learning orientation, C prof, and then also problem solving all in one line. But that can't be the case here. So if you had one line and put a 1 next to it, it would make learning orientation, C prof, and problem solving all equal across the groups. So in other words, if your beta was, it'd make all betas, let's say 0.2, 0.2, 0.2, and then not only are those equal across within the sample, but across the sample. So again, it's very important that you have one line per parameter constraint. if you look back at the original figure earlier on, you'll notice we estimate 6 path coefficients, 1 for every number. So again, those are going to be fixed, or constrained is a better word, constrained to be equal across the pay and no pay groups. Our next step then is to determine whether the path invariant model is different from the configural invariance model. In other words, is there a significant difference when you constrain the paths to be equal across the groups and when you don't constrain them to be equal across the groups? Here we can see that our configural invariance model with 8 degrees of freedom has a chi-square of about 20-21, where our path analysis invariance with 14 degrees of freedom has a chi-square of about 16. Again, look at the degrees of freedom, they changed by 6. It's 6 because we now have 6 parameters that are constrained to be equal across the groups. In this case, we care about a couple things. Most importantly though, we want to know, does our changing chi-square, is that significant, meaning that groups are non-invariant, or at least one path coefficient differs across the group, or are they invariant? Invariant, again, meaning they are equal across the groups. If it's, in this case, our path coefficients are invariant, because our chi-square is non-significant. Again, this means our path coefficients are equal across both groups. In other words, the prediction of each x on y doesn't vary whether your parents pay or do not pay for college. Because the change in chi-square is non-significant, we can stop here. However, if the change in chi-square was significant, we then look at the modification indices and figure out, okay, which path coefficients differ across the groups. And again, it's important to remember you only want to relax those path coefficients that are constrained to be equal across the groups and nothing else related to the model. We will now spend some time in class and provide a good example of how and when you would use this.